start officers. Okay, so you said you didn't have any specific questions, Shauna? Did you have any particular questions for me, Good Doodle?
Um, I didn't get to the. I'm assuming that in the video you guys went over the word, right?
Over the
Like
what?
over the string.
Yeah, over the one
Part
with
of
the
the homework.
string, the one that had
Okay, yeah.
fall and winter. Yeah, we went over that last time.
hmm
Yeah.
I'm assuming it's just that we just need to remember that the char is just one byte rather than four, and then but it's any type of like iteration.
Yeah. Yep.
Okay.
And she actually gives. We didn't realize this until partway through, but she actually gives you the code to initialize the strings. You just have to know how to traverse the array itself. But she already gave you the
Yeah.
code to initialize them. So.
Were you guys making that?
Yeah, we did it. We did it by hand for like the first word.
It was good.
Yes, it is helpful just to see why, but it mostly just comes down to store the byte in a register, and then store that register value to memory, and then repeat that, however many times for however many characters you're doing, and that's it. So it's a lot of code, but it's not, and it's important to know how to do it. But once you know how to do one, you can do it as many times as you want forever. So not too bad. Did you have any other questions?
Mm. She went a little over thread pointers. Is that having to do with like the threads of your CPU, or is that?
Yeah. Or at least that's
Okay.
one thing they can be used for. So, like, you have a few of your registers that are dedicated to specific tasks. So, for example, the easiest example to think of is the 0 register. It's dedicated to the task of holding the value 0 at all times. And then you have another one, which is the next register right after that, which is RA. That's the return address register. And its sole purpose is to be used to store return addresses for function calls and jumps and stuff like that. Though, while that may be its intended purpose, you do have the flexibility to, when you're writing your assembly code, do function calls without using RA. You can actually use other registers. So you have the ability to do that. It's just standard practice if you're doing RISC-V to use RA for return addresses, and to use the next few, like the stack pointer and the global pointer, to point to specific indices in program memory, which correspond to your stack and then your static memory allocation spots. So yes. I see a question forming.
I was like, just thinking. Just, yeah, no.
Okay.
All of the return address stuff is automatic. We like have to.
In terms of what? Like, what part of it is automatic, do you mean?
Like, it knows what address. Like, it takes the address of like right after the JAL statement, right? Like, we don't need to specify. It's the PC.
Yeah, so when you do JAL, yeah. So you just have to tell it where you want it to jump.
Yeah.
It's going to handle remembering where to come back to when you return from there.
Yeah, because like the slides say the actual memory, and then I was like, but I don't think we need to like specify. I think it's just to show us.
No. Yeah, because the value that's going to be stored in the return address register is going to be the address of the instruction right after this.
Yeah.
Because that's where you're going to return to, the spot right after this.
The PC.
Yeah, so if this is the current PC stands for program counter, that's where you're currently executing at, then it's going to remember PC plus 4. That's what it's going to store in the return address register.
So I think my question was like, I didn't realize the instructions we do in RISC-V all have a memory associated with them.
So as a question to you, you guys have you guys gone over the encodings yet? Okay, that's fine. You'll go over them eventually, like soon.
I don't know.
So like, if I told you this, you could write this in 32 bits. Like, this can be expressed in 32 bits of binary that corresponds to this exact instruction.
Is that the machine code?
Machine code, yes.
We looked at it in Venus, and Dr. Harris is like, we'll talk about that later.
Yes, you will.
Yeah, because it's like, yeah, the.
Okay, so I have a question for you. Where is the machine code? Because that's information, right? That corresponds to your instruction that you're supposed to be executing. But you need to store that somewhere, don't you? So you need memory space available to store that.
Oh.
And so
It's in the lowest. Is that the lowest part of the
depends.
stack
It
or
depends
something?
on your. No, it depends on your processor. It really just depends.
Okay.
But in general, it's located in a memory block. But if you have a memory block, you have addresses that correspond to which parts of memory you're referring to. So every instruction is stored at a program memory address.
Right. We did. Yeah. And then in Venus, I want to say it was like at the bottom in Venus.
I have no idea. Probably, it probably is at the bottom.
Right,
Yeah.
yeah. And then it was like, oh, okay, so you need to like make your base memory like higher up so it doesn't run into. But I might be confusing with staff. We talked about staff today.
Yes.
Anyways, stop for a second.
No worries. Yeah, so PC here is a register. It's just a 32-bit register that corresponds to the the 32-bit address of whatever instruction it is that you're currently executing. So again, this is a separate memory from the registers that are in your register file, like S1, S2. It's separate from those. It's a separate memory unit that holds the program instructions. And it could actually also be combined with the data memory, which was the memory unit we were talking about before. Those could be combined data and program memory. That's fine too. You would just have them in different indices of addresses. Like you have this specific section just for program memory and this specific section for data memory.
Yeah.
That's a common thing. Just so you have one cohesive like unit of memory. Okay, someone else came in the Discord. Did you have any questions for me?
I'm not sure if you went over this already, but can you go over E of the homework?
So yeah, we went over that one last time. So if you want, you can look at the recording. But if there aren't any other questions, I don't mind going over it again. I will say though that in the instructions, like below the problem, she actually gives you the code to initialize the strings. So you don't have to worry about doing that. It's already written for you.
Okay, then can we go over F in that case?
Yeah. So let's see. Question F. Yep. So that one is the one which goes with function calls. Yes. Okay, so okay, well I'm going to assume everyone has it available, so I'll just read off of the code and start writing some of the assembly stuff. So you have your main function, so I'm going to have just a label here called main. And then my main function is contained within this, so I might have some assembly instructions up here. And then I have my function call. And my function call is the line where it says int y equals subtract of 7, 3.
Why do we label it main if we don't like jump back to it? Like, do we
Someone
have
calls
to?
main. And when I say someone, I mean the computer.
I see.
Yeah.
So we do mean it for sure.
Because main is a function, so it must have a label. Okay, so we need to do two things. We need to do a few things actually. We need to call the function, and then we need to store the result of that function in int y. So we need to ask, okay, how do I call a function? Well, you just JAL to the place that it's at. However, you can't forget that you need to initialize the arguments for your function. If your function call has arguments, which in this case there are, you have 2 arguments, you have to initialize 2 argument registers. Typically, this is the practice in RISC-V, you have your first argument in the list stored in A0, the first argument register, and then you have the second argument stored in A1, the third argument stored in A2, and so on. And if you run out of argument registers, then you do it differently, but for the moment, you won't have to worry about that. So what we need to do is, before we do the function call, we need to store a 7 in A0 and a 3 in A1, because again, those are the first and second arguments. So what we'd have to do is we'd say add immediate, and for the first one, again, it's A0 we're using. And we want to store 7 in that register because that's the value we want to pass for the first argument. And it's going to be a very similar line of code for the second argument. The only difference, there's only 2 differences. The first is that we're using argument register 1 because it's the next argument afterwards. And we're storing a 3 instead. So that's just to get my arguments ready, and now I can do my function call now that my arguments have been initialized. So to do a function call, you have to remember that you do JAL, that's always for function calls. And then you always follow that with the label that you're trying to jump to, the label of the function. So here, the function is called subtract. I'm just going to call the label sub for subtract. And that's going to be down here. So after this, after you finish calling the function, you're then supposed to store the result of that function in y. Now, as a question to you guys, in which register is the result of a function call stored? Do you guys remember? Where is my result stored? There's one very particular register that is dedicated to the purpose of being the return value. Do you guys know what that one is?
A0, right?
A0, yeah. So A0 serves 2 purposes. It's the return value, but it's also the first argument register. It's used for both. So what I'm going to do is I'm going to realize that after this function call, A0 holds the value that I just returned. So I'm going to then write that value into, it says we want to store it in S5. So there's 2 ways I can write this. I can do it with a pseudo instruction or with a regular instruction. I'm going to show you guys the pseudo instruction first, just so you know it. It's MV for move. So it's just copying a register value into another register value. So I'm going to copy A0 into S5. So I'm just moving the value of A0 into S5. Do you guys know what actual instruction this would execute?
Oh, we learned this today. We went through some just instructions.
Well, this is basically just saying, so this is what we're trying to do, but you can also think of this as that, right? So you can do it 2 ways. You can do it with add immediate, and then you add A0 to the immediate 0. Or you can do just add, and then you add the 0 register to A0. Then you store it.
So I do have a question.
Yep.
If our functions, like, they don't, it's not like they kill the value of whatever we've stored in the variables after it's done running the way like C++ would. So like, why can't we just use S5 in the function instead of being like, oh, put it in A0 and then we're gonna like come back to this point in time?
Excellent question, yeah. So your function, so there's a few ways to go about this. You have to realize that your function can be called throughout any piece of your code. So it doesn't have to just be right here. It could be called way up here as well, or way down there as well. And at different points in your code, you have different registers which could or could not be holding different values that you do or may not care about, right?
Like G, we call it twice, and one time we're putting it in variable X, and then we're doing Y, and those are different registers. Okay, got it.
So whenever you're doing a function, you always use some registers in order to, do your calculations. You have to use registers. Typically, you want function calls to, you can't always do this, but ideally you'd want functions to only use temporary registers, because remember, the practice is that temporary registers do not have to be saved by the function call. If the main function cared about T1, it's going to save T1 itself and then do its function call if it cared about what was in T1. My function doesn't have to worry about it, so it can use T0 through T7 freely. It doesn't care what came before it. Now, in terms of saving stuff, you save registers on the stack, which I think you guys might have talked about in class a little bit, or at least touched on it. So, if you care about something that wasn't T1, if int main did care about T1, it would store T1 on its stack, and then it would call the function. And now that function doesn't have to worry about using T1, because once we go back to main, the first thing that main's going to do after calling the function is it's going to read back in the things that it wrote to the stack. So it's going to read back in whatever was on the stack for T1 into T1 and overwrite whatever the function call had in there earlier. So it doesn't matter what the function did because it saved the value on the stack. Okay. So that's your code. Again, this is a pseudo instruction. You can do this with an add or an add immediate, and it'd still be the same, just add with 0. And then down here, you're going to have another function, you're going to have your function subtract. So these two sets of code in blue and in red don't have to be close to each other. They could be very, very far away, or they could be right next to each other. We have no idea. So I'm just leaving those dot dots there. Now, for our subtraction function, we only really do one thing. It looks like we just subtract something and store it in a result, where a result is S7. You'll notice here that my function changes an S register, which is a saved register. Here, she says, don't worry about the stack in the assignment, but if it was a real function call, this, the function, needs to save the main function's S5. The S registers are required to be saved by the callee. So when I say the callee, that means the function that just got called. Main can assume that if it calls a function, that whatever was in S5 is going to be in S5 after the function call. So main does not have to worry about saving S5. If my function here uses S5, it does have to worry about saving it and then giving main back the correct S5. So if I was actually using the stack, I would write save S5 on the stack, do my calculations, restore S5 from the stack, and then jump back to my caller. But here, though, I don't have to worry about that, so I'm not going to. So again, you subtract two things, and the two things are your two arguments, x and w. Well, remember the first argument we stored in A0, and the second argument we stored in A1. So I'm going to subtract those two and store them into S7. And it is x first.
Why don't you just start it using that?
Excellent question. That's what you should do. But the instructions tell you specifically result is S7.
Yep.
But for efficiency's purposes, yeah, remember that we're going to be returning this right now. And because we're returning it, well, the return value has to be in A0. So we would do this, and then we would return. So yeah, absolutely. Instead of doing these two separate instructions, we could definitely just store it into A0 and then immediately return. That would be the, I guess, most optimal way to implement it. Though if we're being completely honest, for a static function call like this, where it's constants 7 and 3, a compiler is going to optimize it, and the compiler itself is going to calculate what the values are and put them in for the function call. So there's no function call actually executed when the code is running, depending on how optimized you want your code to be. It's a little weird to think about, because if we actually think about it, for that particular function call, it calls it with specifically 7 and 3. Those are known values. We know that ahead of time. So instead of running through the function, the compiler can say, okay, wait, I can calculate the function ahead of time because I already know what it's going to be. It's going to be 7 minus 3, 4. So instead of doing this, it's just going to say add S5, 0, 4, which 4 is going to be the return of that function call. So an optimized compiler is just going to do this instead of doing the function call, because it can. It makes it faster to run the code and all that. Anyways, don't worry about that. Just thought I'd bring it up. Yeah, that's it. That's the entirety of F. At this point, after you subtract the two values, you store them in S7, because specifically the instructions say to store it in S7. Then, because you're returning on the next line, you have to have your return value loaded into your return register, which is A0. So S7 gets loaded into A0. Now A0 holds that value 4, the number 4, and you return back to your caller. So that means I return back to the instruction right after I got called, which is here. And then that value in A0 gets moved over to S5. So now S5 holds 4 and everything works as we intended. Okay, any questions on that?
Is there any way you could put the camera a little bit more down? Because I can't see the full.
Down.
Okay.
Or
Thank you.
I can move over too.
In Venus, when you simulate this, when you jump and link sub, and then you finish that call, and then you go to move, and then you try to do a next step, is it gonna go down back to sub, or is it just gonna
it
end?
is.
I had that
Yep.
problem, and I put like a done,
Okay.
a J done in there to like get out of there. Because
Yeah,
it was, like,
yeah.
kept going.
So you would either have to manually step there and stop doing stuff once you get there, or you would have to put a jump done and then jump to like some bottom of the program.
Yeah, that happened to me, and I've realized
You could also return from main. So if you do another JRRA, I think that would exit. So if you right here you put JRRA, it's going to return to whoever called the main function. And I think that would also end Venus. So you can do that too. But yeah, you're right. If this was just all you wrote in Venus, it would totally just go straight down here. Yep.
so vexing.
Any other questions? Okay, are you guys alright if I erase this?
Yes, thank you.
Yeah.
Alright. Any other questions for me?
I think I am just a little confused about like the preserved versus non-preserved in a function. So like the S saved registers are preserved. Does that mean when you're in the function, if you change S5 and then jump back to main, S5 will still have that value, right? Or no, that's when you have to actually specify the stack, like to save it in the stack, right?
So if it's a preserved register versus a non-preserved register, that just indicates who is in charge of saving it, because it always needs to be saved if you care about that value. It just depends on who is going to do the job of saving it.
Okay. And so calling.
Yes. So callee versus caller. So callee is the function that I'm calling. Caller is the guy who's calling that function.
which is
main,
main.
in all of our cases, main has been the caller, and in the case you were talking about, subtract is the callee. But what if subtract had another function call inside of it? Then subtract would be the caller, and the function it's calling would be the callee.
And you need to put your saving the stack inside.
And so then it depends, yeah. So if it's a preserved register, or I like to call it a saved register, that means that the callee is in charge of making sure that register has the value it originally had. So if originally in main, I had S5 was equal to 7, and then I did a call for a function. After that call, S5 had better still be 7. Main knows that because this is a saved register, it's an S register, that it doesn't have to worry about the function that it calls. The function that it calls is going to guarantee that even if it uses S5 in its function implementation, that it's going to restore it to whatever main had after it returns, right before it returns.
Okay. So if for some reason your function did change S5 after you jumped out of it and you return address back
So-
there, it'll just revert to 7?
It won't just revert to 7. You have to do that manually in assembly code. I'm saying this isn't something that the hardware does. This is a software engineering practice. So we have to remember as the coders that these are the typical practices, and so we have to remember to do them.
Oh, I see.
So it's not something that's done in hardware. It's purely something that we would code up. I'm saying just that's what we want to do. Okay, so that's for preserved or saved. So in the preserved case, then the callee, which in this case, in the case we talked about before, would be subtract, the subtract function. This guy has to save S5, do whatever it wants to do, restore S5 to its original value, and then return. That's all. Now, in the non-preserved register case, so for example, the T registers are an example of a non-preserved register. Here, if main cared about T1 before a function call, main would be in charge of saving it. So main would have to say, save T1 on the stack, and then it does its function call, and then it restores T1. And then now T1 is equal to 3 again. Here, though, the callee is not in charge of keeping track of what T1 was ahead of time, so it can just do its stuff, even if it messes up with T1 and then return. So the only difference between preserved and non-preserved is who's in charge of saving it. If it's preserved, the callee has to save it, and if it's non-preserved, the caller has to save it. That's the only difference. And again, it's not something implemented in hardware, it's a software coding practice.
That makes sense. Thank you.
All right, so any questions on that?
And is this just like if you like run out of variables or like registers? Or something?
Yeah, like what if my function uses all the registers?
Yeah. Okay.
Yeah?
Otherwise, you would just avoid using like.
Yep. You
You
wouldn't
just
trouble
use your
yourself
keys.
because it's extra instructions. Exactly.
Got it.
Yep. Okay. Are you guys alright if I erase this? I'll take that as a yes.
Yes.
Okay. Any other questions for me?
When we initialize the stack pointer, we need to use minus intermediate, right? Because the stack that's at the top of the stack, or like what we have, is at the top, and then creating new is going down.
Yeah, so whenever you enter a new stack space or like a new function scope and you want to start your new stack, you have to start by decrementing it because the stack pointer points to the bottom of the previous person's stack. So you can't start writing by there. You have to go down one, and then that's your starting spot for your stacks. And yeah, it's going down. You subtract by 4. You subtract by specifically by 4 because remember the addresses go down in units of 4. But you're subtracting, you're going down because the stack space actually grows downwards. So it's backwards from what you think. It starts at hex like 7 all Fs, and then it goes hex 7 all Fs C, and then hex 7 all Fs 8, and so on. So that's how the stack grows. But yes, when you're initializing your stack pointer, the very first thing you do is you decrement by 4 because you want to get to your new own stack space. If you don't decrement by 4, you're overwriting the previous guy's stack space. Because you could, if we don't know, but you could be, you know, like the 4th function in like a recursive function call or something. And so, you know, you have 4 stack spaces above you. And if you write at the wrong spot, oh, you just messed up all the stacks now. Or that bottom stack at least.
And because we decremented by 4 the first time, we would need to increment by 4 again when we're done with that.
Correct. To restore the stack pointer to where it originally was. And maybe you're not just storing one thing on the stack. Maybe you're storing 4 things on the stack. So instead of decrementing by 4 once, you have to decrement by 4, store, decrement by 4, store, decrement by 4, store, decrement by 4, store. And then when you're about to exit, when you're about to return, you have to read from the stack, restore it to a register, read from the, and then go to the next part. You have to add 4. So you read from the stack, restore it to your register, increment by 4. Read from the stack, restore it to your register, increment by 4. And so on until you clear up your entire stack space and return to where the original user's stack was. So you just undo the process you did.
Could we do an example of why are we restoring?
So on what I drew on the board,
Yeah.
remember how the callee, like when I had the preserved registers, the callee had to save a register, do its calculations, and then restore the register so that main could have the value that it wanted? That's what I'm referring to, the saving and the restoring part. Or are you asking me how to write that?
No, I think I'm like confused because like the deallocating the stack space is when we're going back up to the top of the stack or whatever.
Yeah, the top, it's called your stack frame. That's how much stack you used. So the top of your stack frame.
And that's the when we add however many down.
Yeah, so if we went down by 8, we'd add up by 8 again.
Like what is this for? Like what exactly is that?
Okay,
code word?
so take a look at this. That's storing to the stack, and this is reading from the stack to restore.
To get it back in.
Yeah.
Okay.
Yep.
Yeah.
Mhm.
And then we deallocate, and then we drop it. Cool. Okay, yeah, because in between we changed S3,
Yep.
and now we need S3's original.
Any other questions?
Why are we calling it a leaf function and then a
So a leaf function, you can think of like a tree. So it's called, I think it's called this because of trees and stuff. But a leaf is the stopping point of growth, right? If you have a branch, things can come off that branch, extra branches, and then leaves can grow off those. But the leaf is the ending point. Nothing grows off the leaf. So we call it a leaf function when that function doesn't call anything else. So if my function that I'm currently in doesn't do any calls, it's a leaf function. Because the only thing it can go is go back up where it came from. It can't go further down into the function calls. It's a non-leaf function if it does have a call within itself. Yeah. Any other questions? Am I doing that good of a job, or are you guys so confused you don't even know what to ask?
No, you're doing a really great job.
Thank you.
This is not
I mean, if no one has any more questions, is there any way you could go over E again?
Over which one?
E?
Sure, yeah, we can talk about E. So again, for E, remember that she gives you the code to initialize the strings. So all that code would just be at the top of whatever the next code I'm going to write on the board is. So all of that would be at the top. And I'm just going to write a few things on the board. So, and these are just like notes for me off to the side. This one is equal to under. Okay, so I just wrote a few notes on the board. Specifically, it was just which registers correspond to which variables in the code. So we're using S1 through 3 for the 2 length variables, as well as to determine which is longer. And then we are using T1 and T2 to correspond to the base addresses of the 2 arrays we have, text1 and text2. Okay. So any questions about the comments I wrote before I get into it?
No question.
Okay. So again, like I mentioned, those first 4 lines of C code were already implemented by the code that Dr. Harris gave you guys. So you just put that at the top. And then the next 2 lines after that, which would be, let me actually check to see if she hasn't also, no, she has not. Okay, so the next 2 lines after that, where she initializes length 1 to 0 and length 2 to 0, that's where we're starting. So we have length 1 equals 0, length 2 equals 0, and that's as simple as just saying add immediate 0, 0, and we're done. So the first 2 lines of code are going to be and then it's length 1 and 2. Okay, and I'm going to purposely do something here. And I want to ask you guys, what is wrong with what I just wrote? Because what I just wrote is wrong. If you tried to type that on Venus, it would give me a little squiggly line.
Wouldn't you have to put like the number 0, like the digit?
I'm doing an add immediate, yeah. So this needs to be an immediate value. I can't use a register twice. If I used a register twice, it'd have to be the add function, or add instruction. Alright. Okay, so that's the first 2 lines of code, probably the easiest lines of code you guys will ever write in assembly. And now we're going to have 3 kind of units. We're going to have a while loop, and then a second while loop which is identical. So I'm actually just going to write the code for one of them. And then the other one's identical, you just switch around some of the registers. And then we have the if statement at the end. So I'll go ahead and write the code for the second while loop, because I think I did the code for the first one last time. So I'll do the second one this time. So for that second while loop, I'll go ahead and write that on the board as well, just so I don't have to keep looking back and forth. While text2 is that length. Cool. Okay, so that's the C code, and I'm going to go ahead and explain what this is doing before I translate it. So it's a little difficult to tell what the code is doing, but I'll, off at first glance, but it's not too hard to understand once I go through it. The point of this code is to find the lengths of the strings that you have. And then once you have those lengths, you can compare them to see which string is longer. So that's why the variable names are length 1, length 2, and longer. So what this while loop is doing is it's actually calculating the length of the second word that we use. So the second word that we use is the word winter. That's the one that's stored in text2, or the string, sorry, I keep saying word. So the string that we had in text2 is the string winter, and it's length 6, because there's 6 characters in it. And so this while loop is going to calculate the number 6. That's what we expect it to return. Okay, so I'm going to go through the code of how to write this part up here. So for that one, we have a few things we need to do. We have a while loop, so I'm going to call this, let's say, while 2, just because it's a while loop, but it's my second one, so I'm going to name it while 2. This is going to be the contents of my while loop, and I might have some initialization stuff above it, so that's why I've left a space here. So I know that when I'm inside my while loop, I want to increment my length. So what I can do is, well, actually, how do you increment a variable? What code would I write to add 1 to something?
add immediate S2, S2, and then just one.
S2, and then S2 1. Yep, that's right. So I would say add immediate S2, 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 1. And then after I increment, I can just go back to the top of my while loop. So I can say jump while 2. Okay. Now I'm also going to go ahead and have a temporary register, because while I've written this, there's actually one extra thing I need to have in my while loop. It's going to have to do with the iteration of going through each index in my array. So I'm actually going to erase this and have a little more space. And I'm also going to use a temporary register for it. But we'll get to what that is that we're going to change in just a second. So I'm going to use a T3. And I'll say what that's going to be in just a minute. Okay, so for my code, I need to, before I even get into the while loop, I need to know what my thing is inside those parentheses. And every iteration, I need to figure out what that thing is inside these parentheses. So I need to be able to evaluate this. And so then the question becomes, well, how do you fetch this value? What assembly instruction would I do to find this value or to get that value? And I don't mean like the full code, I just mean what instruction in particular should I use. What do you think, Lou?
Get some instructions for the while loop.
Specifically, what instruction would I be able to execute in order to get this value here?
Is it load word or store word?
Yeah, I want to load from memory. But in particular, it's not going to be a word. And so this is an important point. Remember that these arrays are actually going to be character arrays. I didn't write it on here, sorry. But in the code, you'll notice that they're character arrays. And characters are not stored in sizes of a word. A word is 4 bytes long. Characters are actually stored as 1 byte, which is 8 bits long. So keeping that in mind, since we're only loading in a single byte, instead of doing load word, you would do load byte. So you do LB for that. Okay, so what I'm going to do is I'm going to go ahead and do my load byte. Now, I'm going to be loading my byte into just something that I'm going to be checking in my while loop. I don't care what it is that I load it into. I just need some sort of temporary thing to hold it. So why don't I just use T4 for that purpose? So T4 is going to hold whatever we read from memory. Now here, I have to be careful because we need to keep in mind that every iteration of this for loop, we're not reading the same thing. So I can't put like a static number here. I can't just put a register that's unchanging. So I can't just put T2 because T2 is constantly hex 220. It's always going to be that. I need another variable to keep track of my base plus whatever offset I'm currently at. And that is what I'm going to be using T3 for. That's going to be the full address I'm looking at. And so what I'm going to do is I'm going to say, okay, I'm going to use T3 for this purpose. So above this while loop, I need to initialize T3 to the base address because it needs to be that before I begin the while loop. And the base address here is stored in T2. So again, all I'm doing is I'm basically storing the base address plus 0, so just the base address, into T3. Again, you could write that as a pseudo instruction, move T3, T2, and that would work as well. Yep.
Is there any sort of instruction we could write where we're doing the offset value is a value in a register? Like I know you can't do LB T4, comma, like T8, parentheses, whatever, but I was thinking of like, can you store, like we did with I, and then we're incrementing I 4 times, and that's our offset?
I don't know if there's a pseudo instruction to do that. But if there was, the way that it would execute it is the same way that we do it manually. We have this store the base, and then we add something to it, and then just put that in there and put that as 0. So that's how it would do it if it was a pseudo instruction. Again, I don't think it is, but I don't know all the pseudo instructions, so it's possible. Okay, so with that in mind, we need to now consider the fact that we have initialized T3 to a starting value, which is going to be, what's it called? Yes, the base address, thank you. So T3 currently holds the base address, and then we read in what the value is, the character at that base address is, and then we have to check something. So we need to check the condition of the while loop. And this is a very confusing part if you don't understand exactly what the syntax implies. So whenever you have a conditional statement in C code, something inside these parentheses, you have to evaluate whether or not that inside is true or false. So when I say true or false, what that means is it's only false if this evaluates to 0. So if this is a multi-bit number, it has to be all zeros. If any individual bit in this number is 1, it's going to evaluate to true. So all this is doing is it's looping forever, and it's going to stop once the inside is equal to all zeros. Now, I also want you guys to remember that we have character arrays, and these character arrays are assigned string values. And strings in C code are terminated with the null character. The null character is the character which corresponds to all zeros. So all your other characters, A, B, C, D, less than, greater than, all those, have non-zero values. Some of them are hex 60, hex 75, hex 13, all those. But the null character is the only one which is hex 00. It's all zeros. So when you read that from your character array and you put it here and you check against the while loop, the while loop's going to read it and say, okay, I just read in a character and it was all zeros. Well, I interpret that as false. So I'm not going to continue looping and I'm going to exit. So in other words, we're going to leave my loop if this is 0. And in other words, we're going to branch if this is equal to 0. So that gives us a hint as to what assembly instruction we should use. Branch if equal to 0. Now, that is a pseudo instruction. There's a pseudo instruction that's literally just branch if equal to 0, but that gets implemented as follows. So we branch if equal, and the two things we're comparing are this, which we said was stored in T4, and we're comparing it to 0, which is stored in the 0 register. So I can just say 0.
We can't compare it to an immediate, right?
Nope. Yeah, you have to compare two registers. So if you wanted to compare it to an immediate, you'd have to load that immediate into a register, and then you can do the comparison. The only reason branch if equal to 0 is a pseudo instruction is because we have a register which is always 0. Okay. And then we would say branch to, I guess, end. So this is saying if T4 is the number 0. So if we read in T4 and it happens to be the null character, that means it's all zeros. So it's equal to all zeros. But because it's equal to all zeros, we are going to branch and we're going to exit the while loop. Okay. Now I think I missed one last step, which was I need a little extra space for it. Yeah. So I made sure to increment S2, which was my length, but I haven't quite yet incremented T4. So remember that because we're stepping through my character array, I need to make sure that I add add an extra offset every time I go through the while loop. In previous examples that we've talked about, the offset was always +4, +4, +4. Because remember, when you're looking at a full word in RISC-V is byte addressable, which means that each byte gets its own address. And since a word is 4 bytes, you have 4 addresses before you get to the next word, so you have to go up by 4s. That, however, is only for words, because words are 4 bytes long, but since we have a character array here, that's 1 byte long. So we can say the addresses go up by 1s, because it's byte addressable, so every byte gets 1 address corresponding to it. So you go up by 1s here. So if we were doing words, we would have to add immediate 4. But here, because it's a character array, and only because it's a character array, we're incrementing the offset by 1s. Again, because it's byte addressable, and a character has the same size as a byte, and if you're trying to traverse byte by byte, you go up in addresses by 1 step at a time. Words have 4 bytes in them, so you go up by 4s. And finally, I have jump 1, 2, and then I have end 2. And that just about looks right. So, as a recap, this was just the very top of the code where we initialized my lengths to 0. And then I also initialized a temporary register just to hold whatever my full address is that I'm going to be reading from my array. So that's T3. And it starts with the base address. So then I load that address into my register and I check if it's 0. If it's the null character, if it's 0, I'm going to leave because I'm done counting. If it's not the null character, i.e. there's some non-zero character, I'm going to enter my while loop and actually execute the stuff in here. So I'm going to increment my length counter, and I'm going to increment my address counter. So this is my length counter, because remember S2 holds length 2. And this is my address counter, because this is going to correspond to my next address I'm going to read from. If originally T3 held the value hex 220, after going through one iteration, T3 is going to hold hex 220 plus 1. So after jumping back, we're going to be reading from hex 221. So it's going to read the next value to T4, check if it's 0. If it's not, it's going to keep looping, and it's going to do that over and over and over again until we hit a null character and we leave, and now our length has some value. And in the case of this problem, the length should be 6 because the word winter has 6 characters in it. Okay, now that's like 95% of the code. We have like one little thing at the end, which we can do in one simple instruction. But for just this part, are we good? Do we have any questions? Because I know I went through quite a bit. Okay, so what I'm going to do now is I'm going to go ahead and write that last one. So the last set of code, that if-else statement, is quite a nice statement because it lends itself to being implemented in one line. And the reason why, we'll be able to see in just a second. So I'm going to write out the code, the actual C code on the board real quick. Yeah, that's right. So basically all I'm doing is that if the length of my first word is bigger, then I set longer to true, otherwise it's false. So again, like I mentioned, this is just comparing the lengths of my two strings. Okay, now this code can be written in just one line of C code and also one line of assembly. So what I can do is I can say, okay, remembering that spiel before about the inside of the comparison parentheses having to result to either a binary true or false, I can do the same thing here. Length 1 greater than length 2 only has 2 answers to it. It can either be true or false. So this can either return 0 to represent false, or it can return a non-zero value, which we typically just say 1, and it's true. Well, let's think. If this returns true, then we're going to execute the first part of the if statement. So we're going to store a 1 in longer. remember that we think of 1 as meaning true. If this is not true, so if it returns 0, then the else is going to get executed, and we store 0 in longer. So generally speaking, longer is just going to be whatever this returns. Because remember, if length 1 is greater than length 2, this is going to return true, 1. And in that case, longer should be 1. So that'll work. In the case where length 1 is not greater than length 2, it's smaller, then it's going to return false. And in that case, you'd execute the else statement, and so it is false. So this set of code here and this set of code here are the same thing, and they do the same thing, just written differently. Okay, any questions on that? Okay, I'm going to go ahead and write the assembly instruction for this, and I know you guys have probably gone over it in lab, this instruction. I don't know if you guys have talked about it in a lecture, but I'll just bring it up anyways. So the instruction is set less than SLT. So the way that set less than behaves is it compares two numbers. And if the first number is less than the second number, then it sets the destination register. And when I say set, I mean it receives the value 1. If the first register is not less than the second one, then it sets it to 0, which is exactly what we want it to do from the if-else statement we saw earlier. However, because this is a set less than, I'm going to write this in terms of less than, the less than operator, because this is the greater than operator. You'd read this as length 1 greater than length 2. So I'm going to swap the order. This can be read as length 2 less than length 1, or length 1 greater than length 2. So either way, it means the same thing. It's just syntactically, this is the less than operator. So that's what I'm going to use. So I'm going to store the result of this computation in longer. That's the destination register. And longer was S3. So S3 is going to be 1 if length 2 is smaller, and it's going to be 0 if length 2 is bigger. And so then the next two things you put are going to be the actual registers that correspond to these two. So length 2 is going to go here, and that is S2. And length 1 is going to go here, and that is S3, or S1. So all this is saying is if S2 is smaller than S1, you're going to make S3 the number 1. And if S2 is not smaller than S1, you're going to make S3 the number 0. So this one line of assembly code means and does the same thing as that if-else statement that was in the given C code. You could absolutely do it just by, doing jumps and then checking a condition with the branch statements, and you get, 4 or 5 lines of assembly code. And there's nothing wrong with that. You can absolutely do it that way. I'm just showing you another way to do it because, well, this is a nice instruction to know if you want to write, if you want to do less thinking and more code writing. Okay. So again, we discussed that the character array initializations was already given to you. We talked about how to do one of the while loops, and the other while loop is identical, and I did it yesterday. And we talked about how to do the if-else statement at the end, which is just a set less than. All right, so with that kind of discussed, any other questions for me?
No questions from me. Thank you.
Okay. You guys all right if I erase this from the board?
Yeah.
Okay. I'm going to go ahead and, I'll go ahead and end office hours. Remember that I changed my office hours tomorrow, on Friday. Not tomorrow. Tomorrow's Thursday.
Office hours, even though the school's closed. It's Nevada Day, right?
Oh, that's right. I don't know. Probably don't come to school, I think. Yeah. Never mind. So no office hours on Friday. Though on Fridays in general, just remember that I changed them from 10 to 11 online to still here, but from 2:30 to 3:30. All right, cool. Thank you guys for coming in. I'm going to go ahead and stop the recording.
Yeah, that
Thank you very much, Victor.